Alright guys, so here is my step-by-step on how to do all of the practice problems for exam number 2. Um, just for clarity. Okay, so let's go ahead and get started. So choose a pair of names and formulas that do not match. So what I would do if you're not sure if it all looks right, I'm going to go ahead and break down every single answer that can be broken down and explain why it is or is not right. So starting with number 1A, copper 1 nitrate. Copper 1 tells us that it's Cu plus, and then from knowing the polyatomics, we would know that nitrate is NO3 minus. So when we do the swap, it would just be CuNO3, and that checks out. So that's right. Going to the next one, copper 2 nitrate, nitride, Cu2 plus, and then you know what nitride is? If you said N3 minus, you would be correct. If you swap the charges, that would give you Cu3N2, which is what it has on there. Perfect. Alright, so let's go to the next one, copper 2 nitride. So that's Cu2 plus. And then nitrite is like nitrate minus 1 oxygen. So NO2 minus. That's going to give you CuNO2 2. Right? And that's exactly what we have. So that gives us the answer D. All of them are correct. Alright, so for the next one, how many molecules of sulfur trioxide are in 78.0 grams of sulfur trioxide? So first we need to figure out the molar mass, and to do that we're going to have to find the formula. So the formula is going to be S for sulfur, and then we're saying trioxide, so that's going to give us O3. So to find out the molar mass of this, we're going to go sulfur and oxygen. We're going to go 3 times the mass of oxygen. So the mass of sulfur, according to my periodic table, these are all in grams per mole, 32.06 grams per mole, and for oxygen, it's 15.9994 grams per mole. Remember to multiply this by 3. That will give you a molar mass when you multiply this out and then add this to it. That'll give you a molar mass of 80.0582 grams per mole. So when we do that, or we have that now we need to figure out the molecules. So to figure out the molecules, we are going to go 78.0 grams of SO3, and we're going to take that and multiply it by the molar mass. So 80.0582 grams of SO3 and 1 mole of SO3. And then we want to find out how many molecules. So we know that 1 mole of anything, in this case SO3, is going to be Avogadro's number. So 6.022 times 10 to the 23 molecules of SO3. So when you do that math, let's do a quick unit canceling. Grams of SO3, grams of SO3, moles of SO3, moles of SO3. Our units are going to be molecules of SO3. And when you do all that math, you get this number. And just a heads up, I've done the math before, so you don't have to sit here and listen to me punching numbers on the calculator. So we get 5.867 times 10 to the So when you round that number, the 5.867 7, that's going to round up to this number right here, which gives you that. Let's say you happen to get like 5.85 times 10 to the 23 or something. You're not going to choose none of the above. You're close enough to this one to choose that one. So that makes all of these other ones incorrect. Okay, the correct orbital diagram for chlorine. So chlorine is number 17. And if we just read the periodic table, we're going to have 1s2, 2s2, 2p6, 3s2, 3p5 in this case, because that's where it stops. And then if you wanted, you can see on her printout, she did it with the arrows. This means the same thing as that. Alright, so that gets number 3 out of the way. Let's go to number 4, slowly but surely. I'm going to split this into 2 videos too, because I can tell it's going to be really long by how long it took me to actually do all of these problems. So just a heads up on that as well. Alright, so which is incorrect? So for A, magnesium nitrite, so we have Mg2+, and then nitrite is NO2, NO2 minus, so when we put these together, that's going to give us Mg NO2 2, and that's correct. Okay, so we want to look at calcium carbonate now. That's Ca2 plus, CO3 2 minus. Put those together. That's CaCO3. That's correct. That matches what we have there. Alright, so for the next one, we have aluminum sulfate. Aluminum is Al3 plus, sulfate is SO4 2 minus, right? So when we swap the charges here, we're going to get Al2 SO4 3. Well, if you look here, we have Al3 SO4 2. So that is going to be the incorrect one. And just for reassurance here, if you guys have a hard time remembering hydrogen carbonate or bicarbonate or any of like the hydrogen sulfate, dihydrogen phosphate, I thought of another way that you can look at this. You can look at it as, okay, sodium from that, hydrogen. Hydrogen can be H plus, right? If it's hydride, it's H minus. So H plus and then CO3 2 minus. So if we put all this together, we have a total of 2 positive charge and 2 negative charge. So we can see that that's just going to be NaHCO3. And that's exactly what we have there, so that's correct. So basically what I did here is just remember carbonate, and since we have hydrogen, we only have one of them, that adds another positive charge there. That's just another way that you can look at this stuff. Okay, so number 5. This one's one, it takes just a little bit longer to calculate, but it's not actually all that bad. So the value of N. So you know that your N is going to equal the, not the empirical, the molecular formula divided by the empirical formula. Okay, so what we need to do here is find out the empirical formula of this, and we're given our molecular formula, MF. So, to find this out, we have carbon, we have 3 times, and this is in grams per mole, 12.011. And then for hydrogen, that's going to be 5 times 1.00794. When you add those together, you will get a mass of, looks like it says 41.0727 grams per mole. So now we're going to take the 205.40 grams per mole divided by our 41.0727 grams per mole. Notice how our units cancel in this one. And that's actually going to give us 5.000 and then more numbers, which means our N is going to equal 5. And that gives us this number right here. You can do a quick check on this too. Once you have this, if N was 10, you would multiply this by 10 and you should get that mass. Well, if you multiply this right here by 10, you get 410.727 grams per mole. That's way too high. Well, if this is too high, that's too high. So that would leave you with these two choices right here. That's another way to double, triple check yourself if you'd like to do that. All right, on to the next one. A mass percent of sodium and sodium hydrogen phosphate. Okay. So sodium hydrogen phosphate. So sodium, and then we have hydrogen phosphate is H, and then PO4 3 minus. So hydrogen phosphate is actually HPO4 2 minus, right? So our formula is going to end up being, hold on one second. Sorry for that little interruption. I know it's not going to seem like much to you guys, but my daughter's sick and she just threw up, so I had to kick rocks for a couple seconds. Alright, so, what was it? Okay, so sodium hydrogen phosphate. So now that brings it down to a -2 charge. So Na is going to be, Na2 HPO4, right? Because we need a total of 3 negative charge, so 2 from sodium. You can't add anything to this hydrogen. If you do, it goes from sodium hydrogen phosphate to sodium dihydrogen phosphate. So we want to keep this polyatomic the same, so it's Na2PO4. So we want to find out the percent sodium. So we need to figure out how much sodium there is. So let's do this. So we're going to take the molar mass of sodium and multiply it by 2, right? Because there's 2 of them in the compound. So it's going to be 2 times 22.98977. And then hydrogen. We're going to make a note of this because we're going to need this separately. Because we want to know the percent sodium. So a mistake that can be made is somebody just putting the 22.98977 over the total molar mass. Remember, there's twice as much sodium in this compound. But okay, for hydrogen, it's 1.00794. Phosphate, that is that mass. And then oxygen, there's 4 times the mass of oxygen, which is 15.9994. This gives us a grand total of 141.95884 grams per mole. But when we do this separately, we get a total mass of 45.97954. So we want to make sure we have that off to the side. Okay, so to figure out the percent sodium, to do this, we're going to need, so percent Na is going to be the total amount of sodium over the total molar mass. So 45.97954 grams per mole over this total mass. And we need to multiply that by 100. When you do that, you get 32.3893%. The number keeps going, but it's going to be in 3 sig figs, so 32.4% sodium. That would be our answer on that one. Cool. So, the next one. What is the formula for an ionic compound made of barium and nitrogen? So, we have barium, which if we look, it's a group 2A, so that's going to be Ba2+. And nitrogen is what? It's in group 765A, so that's actually going to be 3-. That is going to, 3-, sorry. So swapping charges, that's there, that would give us Ba3 and 2. No reduction can be done, so we are good there. That would be our final answer. Sorry, I'm checking something. Okay. So back to this. Alright. So we have a 55.5 gram sample of magnesium nitrate. How many atoms of nitrogen are within this? So first thing we need to do is turn this into something useful. So magnesium nitrate, that's going to be Mg2+, and then nitrate is NO3-. So that's going to give us the the formula of MgNO3, right? Swapping charges. So we need to find the molar mass of this as well, because we're talking about this size of a sample, and we want to turn it into atoms. So we need a conversion factor here. So when we do that, let's go ahead and move off to the side a little bit. Mg is nitrogen is going to be 2 times 14.007. Oxygen, there's 6 total oxygen here. That's a place that people will tend to make mistakes. So make sure you remember that. There should be 3 9s. When you add all of this up, you get a total mass of 148.3154 grams per mole. So, let's go back over here. Too far over. Okay. So we have 55.5 gram sample of MgNO3, and then we're going to use the molar mass to find out how many moles of magnesium nitrate. Once we have the moles of magnesium nitrate, we can use the ratio. For every 1 mole of this, there's going to be 2 moles of nitrogen, right? Because of the 2 gets applied there. And then from there, we can use Avogadro's number. So, 1 mole is 148.3154 grams of MgNO3. Sorry, that's all squished in. That's 1 mole. MgNO3, did it again. Sorry. 1 mole of MgNO3. So that's going to give us 2 moles of nitrogen, right? And then for every 1 mole of nitrogen, there is 6.022 times 10 to the 23 atoms of nitrogen. So when you are taking this next test, I highly recommend putting Avogadro's number in on the storage of your calculator so you don't have to type this. I know overall it'll probably save you like a total of, I don't know, 1 or 2 minutes on the test, but that's 1 or 2 more minutes you can use to go over other stuff. Also, when you're taking the test, anytime that you calculate a molar mass, make sure you have it written somewhere where you can get to it quickly, because you might have something asking about the same compound later on. Just thought I'd throw that out there too. So you'd have a quicker reference instead of having to go back and calculate it again. Okay, so when you do this math, let's do a unit check real quick. Grams of magnesium nitrate, moles of nitrogen, and we're left with atoms of nitrogen. Perfect. And then when we do the math, we get 4.5068 times 10 to the 23 atoms. So sig figs, 3 sig figs from here. That would give us 4.51 times 10 to the 23 atoms of nitrogen. That would be our final answer right there. Perfect. Okay, so this one is the one that's going to take the most paper space and or time to do of this first video. Okay, so we know vitamin C has this formula right here. We have to figure out for X, Y, and Z. So we first have to figure out its empirical and then its molecular formula. We'll figure out its molecular formula using this, and N equals the molecular formula divided by the empirical formula. And that should give us our N value. Then we'll take N times whatever we get for CaHO, for whatever we get as our empirical formula, and that'll give us our molecular formula. Okay, so remember when there's percentages, we're going to assume that we have 100 grams. If we have 100 grams of the substance, then we have 40.92 grams of carbon, 4.58 grams of hydrogen, and 54.50 grams of oxygen. So let's jump into this. So we want to find out how many moles of each of these we have. So I'm going to go ahead and start writing this. When I do these problems, I tend to go ahead and just stick with writing them all kind of at the same time. So I can go ahead and just do all my math at once instead of having to write this, solve it, write this, solve it, write this, solve it. It just saves. This is my personal preference. It's not the 100% way to go. The 100% way to go is whatever makes you happy and gets you the right answer. So, the molar mass of carbon is 12.011, of hydrogen is 1.00794, and oxygen is 15.9994. When you do this math, moles of C, moles of H, moles of O, and that will give us C, whatever, H, whatever, O, whatever. The reason I set it up like this is because you're going to divide by your lowest one, right? So this way you can do the division and then write your numbers right here. So let's go ahead and figure these out. When you do this one, you should get that. Here you should get this. The more numbers you can keep, the better. I recommend just using your storage in your calculator and store each of these numbers until you have the right one, or until you find out what the right one. So we're going to divide all of these by the smallest, and it looks like the smallest number happens to be oxygen, which it usually tends to be. Just thought I'd let you know that, depending on this mass, right? Because look at the molar masses here. We have like 16, 12, and 1. So if this number is about the same size as this one, we're dividing by 16 here, we're dividing by 12 there. That's just something to keep in mind. It's usually going to be oxygen. Not always, but usually. Okay, anyways. So we're going to divide everything by 3.406, 3.406, 3.406. So that's going to give us C1, H 1.33-ish, and then O1. Well, if you remember right, none of the formulas that you've seen or will see this semester are going to deal with point something. So we need to multiply this by something to get the correct formula. And since we're talking about 1 1/3, essentially, I say we multiply everything by 3, right? Because 1.33 is 1 1/3. So when you multiply this whole thing by 3, you get C3H4O3. So this bad boy right here is going to be your empirical formula. So now we need to find out what our N is. And to do that, we need to find the molar mass of our empirical formula. And we're given the molar mass of our molecular formula. So the given for our molecular is 264.21 grams per mole. And then we need to do 3 times 12.011 plus 4 times 1.00794. You'll notice you'll have a lot of these memorized, especially these three. If not by this exam, definitely by the end of the semester. Okay, so when you add all of this up, you should get about this number. So if we take this, the given 264.21, and divide it by the 88.06296 grams per mole, our N is going to equal 3.00 something. So our N is 3. So now if we take 3 times our empirical formula, which is C3H4O3, that is going to give us our molecular formula of C9H12O9. That would be our molecular formula. There you go. So there's those two. So the answers would be C3H4O3 and C9H12O9. Okay, number 10. So let's use a different color here. Alright, so consider the element with the electron configuration krypton, 5s2, 4d10, 5p5. So this element is what? Alright, so the answer is halogen, but let's break it down as to why. If you have a halogen, your thing should end with N being your period, P5. If you look at all of the halogens, so if we're talking about fluorine, it would end, the configuration would end in 2p5. For chlorine, 3p5. For bromine, 4p5. For iodine, 5p5. So in this case, we're talking about 5p5 is what it ends in. So we're actually talking about iodine in this case. So the answer is a halogen. For a transition metal, you are going to get, it should end in something like this. It's going to end in N for your period. It's going to be D because all the transition metals fall in the D block. And then your exponent, or your number up here, is going to be K, where K is going to be 1 through 10. It's going to be any one of these numbers. So you can have like, for zinc, it would be 3d10 is what it would end in. So for zinc, it would be, the full thing would be argon, 4s2, 3d10. But yeah, so it would look like this for a transition metal. For an alkali metal, that is going to be everything that's in group 1. And so everything will be N for your period number, and then it'll be S1. So looking at lithium, that would be 2s1. Looking at potassium, 4s1. Sodium, 3s1. I think you get it now. Okay, so for the actinide, that's the ones that are in the row that says AC. That series is going to look like this. It's going to have 5F and then a K, where K can be 1 through 14. So you can have 5F1, or yeah, it'll end in 5F1, 5F2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 5F14. Any of those will be an actinide element. For a noble gas, what do you think the generic configuration for that is going to be? If you said NP6, you're going to be correct, where N is your period. The other one that it can also be is 1s2. That's another noble gas. That's actually helium. That's like the one exception for the noble gases. Other than that, it's going to be NP6, where if you're talking about period 3, it would be 3p6, which is argon. So 3p6, argon. That's what it's going to end in. Be careful for the exceptions. Those are going to throw you off a little bit, and you'll see that in a second. Okay. So decreasing ionization energy. So ionization energy is going to be the greatest at F, and it's going to be at least at, I just look at fluorine and francium for comparison. So it increases like this if this was the periodic table. So the one with the least amount is going to be the one closest to francium. The one with the most ionization energy is going to be closest to fluorine. So if we arrange this, the most is going to be bromine. That's going to be greater than a astatine, which is going to be greater than cadmium, which leaves tungsten. And if you look at the periodic table, tungsten is going to be closest to francium when we're comparing all of these. All right. Decreasing atomic radius. So we want largest, smallest. And if we're looking, the largest is going to be francium, and the smallest is going to be fluorine. So closest to francium is going to start with Ba, and that's going to be greater than Pb is going to be next. It's greater than Se is greater than F. Obviously, because F is the smallest. So, for the atomic radius trend, it's going to increase like that if you look at the periodic table. Alright, I know this video is super long so far, but we've only got a few more to go before I turn it into the next video. So, which one of the following species has the electron configuration of this? So remember, pay attention to the end first. If we look up to here, 2p6 gives us neon. And so we have 3s2, 3p6, 3d10. Well, we see a 3p6, so 3p6 actually puts us at argon, right? So now we only have 3d8. There's no 4s2, 3d8. There's something going on there, right? Well, we'll look at 3d8. So if we go and look at 3d8, this configuration right here corresponds to nickel by itself. Well, if you look, all of these have a charge, right? So when you're turning something into an ion, you take from the highest quantum number first. If you look, most of these have a 2+ charge. So we're going to go ahead and take these 2 electrons. So nickel 2+ actually looks like argon 3d8. So that leads us to this answer. If we're looking at copper 2+, well, copper normally would look like, let's see, argon, and then normally it's 4s1, 3d10, but we're talking about copper 2+, so that's actually going to get rid of this one and this one and make it 3d9. That would be for copper 2+. We're talking about germanium 2+. That is going to just look like argon. It would normally look like 4s2, 3d10, 4p2, right? Well, we got to take 2 away from the highest quantum number, and we're actually going to take it from the furthest out shell as well. So we're going to get rid of these guys. That would be the configuration for germanium 2+. Zinc 2+. Let's do it in a different color as well, just for clarity. Zinc 2+ would normally look like argon, or zinc by itself, I'm sorry, 4s2, 3d10. Well, if we have the 2+ charge on that, that gets rid of this, so it'd be argon 3d10, which isn't what we have 3d8, right? For vanadium, so that gets rid of all of these. Vanadium 5+. So vanadium is going to look, let's go back to neon. 3s2, 3p6, 4s2, 3d3. Right, so taking 5 away from that, 1, 2, and then this is going to be further out than the p orbital. So we're going to get rid of 3 from here. This would be vanadium 5+. So that's not what we have. So that's not correct. Alright, so number 14. Okay, so this one requires a little bit of thought here. We are going to arrange the following compounds in increasing order of lattice energy. So first thing we need to notice is that all of these have a 2 plus charge. And then these are the same, right? These Cl2s. So that's not going to affect anything. And if they all have the same charge, that magnitude's not going to affect anything either. So for the lattice energy, we need to look at, remember how she said that size, the larger the compound, the larger the compound, the lower the lattice energy. Sorry. Because they're going to have a larger distance between them. So the charges aren't going to be felt as much. They're still going to be pretty good, but yeah. Anyways. So we go back to our trends. We think about francium and fluorine. So francium is the largest, fluorine is the smallest. So as we go this way, the distance, the atomic radius is going to increase, which means that the charge felt, basically the distance is going to increase. So the lattice energy is going to be, oh my gosh, I completely just blanked right now. So increasing lattice energy. So the lattice energy for these, if we're looking at magnesium, calcium, and strontium, the smallest is going to be strontium because it's closest to francium. So strontium chloride is going to be that's going to be greater than calcium chloride, and that's going to be greater than magnesium. Yeah, MgCl2. Maybe I'm saying that backwards then. Because magnesium, calcium, strontium. Yeah, so that's going to require the most energy to get together. That's why I kept messing it up. So this is furthest, this is closest. So this is going to have, it's going to require less energy. This is going to require more energy. Sorry, it's been a long day. Okay, moving on from that. This would be the answer. So we just need to find out what the correlation is between all of these. So we don't really need to worry about chlorine because chlorine's the same for all of these. They all have a +2 charge. The only difference is the atomic size between these. So we use that to find out that it's going to take more energy for this than it is for this than it is for this. Okay. So sorry about that. Like middle of the answer. Loss of consciousness, essentially. Okay. The molar mass of cesium nitride. So cesium, that's in group 1A, so that's going to have a +1 charge. Nitride is NO, I knew it was 2 and I wrote 3 anyways, NO2 minus. So when we put these together, that's CsNO2. Alright, so to find the molar mass, we're going to need to add all these together. So Cs and O. And remember, we have 2 oxygens, so 15.9994. Nitrogen is 14.007. And cesium is the big guy in this, 132.9054. All of these are in grams per mole. So when we do the math here, hopefully the addition is strong with you guys. You get 178.9112 grams per mole. She says to provide the answer to 2 decimal places, so that would give us an answer of 178.91 grams per mole. Perfect. Alright. So this one takes up a little bit more space as well, but it will be the last one that I do for this video. Thank you for sticking around this long. You guys have a lot of patience, and I do appreciate that wholeheartedly. Okay. So let's go with this disgusting color for now. Each tablet in approximate sodium, which is like an ibuprofen essentially, um, or more like an Advil maybe, it doesn't matter, is C14H13NaO3. So I know that I'm gonna need to find out the molar mass because I need to find the percent composition. So C13, or whoops, we have carbon, hydrogen, sodium, and oxygen. Remember, since we're trying to find the percent composition of carbon, we're going to want to write that number off to the side. So we have 14 times 12.011 grams per mole. And then for hydrogen, that's 13 times 1.00794 grams per mole. And then for sodium, that is one I don't memorize. That is 22.98977 grams per mole. Oxygen is 15.99994 grams per mole. When we total that up, you get the whopping number of 252.24519 grams per mole. If you notice too, I keep a lot of the decimal places. That's just to make sure that I get a really good answer. You notice you'll have, it specifically says 3 sig figs, and all of your answers are in 3 sig figs. But still, if you want to make sure you don't get any round off errors, just keep the numbers. It's a lot easier. Also, when you did this calculation, you should have kept this number off to the side. So the copper in this compound accounts for 168.154 grams per mole of this total. So we should have a really large percentage of this. So that kind of gets rid of this and this right out of the bat. Because if we double this number, that's what, 320 something, right? So it's not even 50%. So that leaves us down to these right here. But okay. So let's change from this awful, disgusting color. Tell how much I like that color, huh? So our percent carbon is going to be 168.154 grams per mole divided by, remember this is a multiple choice test, so you don't have to write the grams per mole. It's good to do it because it helps you when you're doing a bunch of other things not to lose your units, especially if you go into 102. There's a lot of units that you're going to have to make sure you remember when you're doing rates. So keep that in mind. So our total was 252.24519 grams per mole. So units cancel. When we do this, we get 66.7%. So if we look, 66.7, number one, it's not anywhere near any of these answers. It's kind of close to this, but that's way too big of a difference. So I would go with none of the above. That would be my answer right there. Thank you so much for sticking through 1 through 16. I'm going to go ahead and upload the 2 videos separately right now. Hopefully make it to part 2. And I won't have the time to timestamp this one, at least not for a day or 2. So if somebody wants to go through and be like, this question's at this time, this question's at this time, before I get the chance to do it, I'm sure that would help everybody out a ton. Well, thanks for watching this part, and I'll see you in a minute.